So what is a conformational isomer? Okay, so it has the same formula. That's that's the definition for an isomer, is that we have the same formula, just an isomer by itself, same formula. So if you have C5H11Cl, if you see two that have that formula, they're isomers, okay? There's 5 carbons, 11 hydrogens, and 1 chlorine in both of the molecules. So the next question is, well, how are they put together? Are they the same molecule just drawn differently, or are they actually 2 different molecules? And that's really how you can tell the difference between these two. So conformational isomers are what? Yeah, they're the same molecule, and it's just drawn differently. But the trick is, remember, if you go through and do the naming for them, so it's the same molecule, it's just drawn differently. But they're going to have the same name. So they'll go through and name them. And when you name them, you can compare them and you should see the similarity. But structural isomers, how are they different than the conformational? They have different names because they have different bonding. So these molecules are put together differently, so they're going to have different names. And the third one, you only see if you're talking about a ring structure or a double bond. And for us, it's just the ring structure, because I'm not going to ask you to name any double bonds. But what do ring structures do to molecules? Make them what? Okay, so making a ring structure is a cyclo. But if you have any functional groups hanging off, what's different about those compared to just a straight chain? That creating the ring means it's going to make a rigid molecule. It doesn't have rotation. So groups hanging off of a ring get stuck in a position. They're either both pointing the same direction or they're pointing opposite directions. That's what stereoisomers are. So these are, in ring structures, non-hydrogen groups on different carbons are stuck. And they're stuck either both in the same direction, both on the same side of the ring, both sticking outward or both sticking back. So they'll either both be like wedges, both be little dash groups. Those they call the one that's on the same side. Those are opposites. So if they're on the same side, that's cis. So if both of the non-hydrogen groups are on the same side of the ring, if they both have wedges or they both have dashes, that is a cis conformation. But if you have one where you have a cis and if you have one that's like sticking out and one that's sticking backwards, then that is going to be trans. And you can think also like one sticking up and one hanging down. So in this, when you see 2 wedges, remember wedges would be like sticking out. So they're both on the same side. So that would be. Another way that you might see that is they also might do this. Stick them both like both pointing up. That would also be considered cis. So they have, otherwise, the rest of the name's exactly the same. So with these, that's a cyclohexane. So that is they are 1,2-dimethyl cyclohexanes because they're on the carbons adjacent to each other. But one you would call cis, the other one would be cis. If we were going to draw the trans, we would have a CH3 down and a CH3 up. Or you'd have like a wedge and a dash to indicate that. So if you look at this first one, all three of these have 5 carbons, 12 hydrogens. Count. First one's 5 across, second one's 4 across and a carbon hanging down. Third one's 3 carbons across, 1 up and 1 down. Well, the first one, its name's pretty straightforward. 5 carbons in a row is pentane. Second one, 4 carbons in a row makes it a butane. And then this is it's a CH3. It's a methyl, right? So remember that the group hanging down, this is a methyl. Oh, you're looking at the last one. See, the first one, there's no non-hydrogen group, so it's just pentane. That's the name. There's everything else is just hydrogen, so you don't have anything else to name with the first one. Second one, we have the butane, but then this group would be hanging off of carbon 2. You would start from the side closest to the non-hydrogen group. So the third one you said is a propane. And then this CH3 and this CH3 makes it a dimethyl. So it'd be 2,2-dimethyl propane. All of these have 5 carbons, 12 hydrogens, so they're isomers. These are all what? Are these conformational isomers, structural isomers, or stereoisomers? These are all structural isomers. They have different names. They're different molecules. They're the same number of atoms, just put together different. And the key thing really is just name them, okay? Because if they got 2 different names, then they're structural isomers. Okay, so if you look at this, 6 carbons in a ring, 2 chlorines hanging off. Those are isomers. They have the same number of carbons and the same number of chlorines. They're going to have the same number of hydrogens. They're just not drawn in, but carbon would always have 4 single bonds. So the base name for both of them is the same because they're really connected the same, right? So you would call them what? This is a cyclohexane. And then those pieces hanging off these are in the first one, yes. But how would you do that? They're chloros. There's 2 of them, so it's dichloro. And they're off of carbon numbers 1 and 2. So you would just say 1, 2, 3, 4, 5, 6. It wouldn't matter if you started and numbered the other direction, as long as 1 and 2 are where the chlorines hanging off are. So the base name is exactly the same, 1,2-dichlorocyclohexane. That's the name for both of those. The only difference between them is on the left side, the little wedges means both of those chlorines would be sticking upward. And the opposite one wedge is sticking up, but the little hash marks would indicate that it's actually jutting kind of away behind the board or behind the plane. So this is the trans. But you're really only going to see that in ring structures. So stereoisomers with ring structures would be the only time you're going to see those. So what about these 2? How many carbons? Okay. Do double check and make sure. How many carbons in this one? How many carbons in the other one? 4. How many bromines? How many chlorines? 1 in each, right? Okay, so they're an isomer. Same number of chlorines, same number of bromines, same number of carbons. So we know they're isomers. And it's not a ring, so you know it's not a stereoisomer. So really, it's the question, is this conformational or are these structural? So this one, longest chain, we said is A. Where would you start numbering from? This is A. Right, so this is a bromo, and this is A. So which way would I number? From the left, because the bromine's hanging off of that end. So this one would be a 1. That's carbon 2, so this would be a 3. Okay, so remember the number tells you which carbon in the chain it hangs off of. So that would be 1-bromo-3-chlorobutane. What about the other one? Longest carbon chain? Okay, so that makes it a butane. Then this is a, this is a, where do you start numbering? Start numbering at the bottom, because that's the bromine's hanging off of that end. So this is still a 1, 2, 3. So these two are, they're exactly the same. They're both 1-bromo-3-chlorobutane. They're just drawn different. These are the conformational isomers. So count the number of atoms in each. If they have the same number, then go ahead and name them. Now, if you count one and you've got 6 carbons in one and 7 carbons in another, then you can just say they're not related. Okay, they're not going to be isomers if they have different numbers of atoms. If one has 2 bromines and the other one has a chlorine and a bromine, they're not related. They have to have the exact same formula, the exact same number of atoms in order to be isomers. So that's really the first step. So you might save yourself some work and just first count the number of atoms, because if you don't have the same number of carbons, hydrogens, and all of the non-hydrogen things, then you know that it's not. That it's a not related one. So where's the other one? Okay, so then the other thing that we were talking about, this is really small looking. I gave you another handout. So we started, we kind of went through them a little fast. So that's why I thought, well, we'll just run through them again. So these are what they call functional groups. So I gave you this. To kind of look at this functional group handout. It's a little laminated. I really need to redo it. It's not the best one ever. But we'll go through them so that you can see the different ones. Really, this is just what groups that you can have when you add oxygens and nitrogens. Okay, so oxygen and nitrogen are sometimes inorganic molecules. It's not just carbons and hydrogens. We're not going to name them. Okay, but I do think you should be able to identify them, to just pick the group out when you're looking at a molecule. So for an alcohol, the way to identify this, if you're looking at an alcohol, is you always look for the OH. The key thing is the OH will be connected to a carbon, and that carbon may have other carbons or it may have other hydrogens, but it doesn't have anything else. Because if it has anything else, then it's not an alcohol. Okay? If there's anything connected, so this could be an H, this could be a C, this could be a C. So you could have carbons or hydrogens. If that's all that's connected to the carbon with the OH, then it's just an alcohol. Okay, so examples of this, like methanol. Or ethanol, sorry. This one's ethanol. Ethanol is like what you get in fermentation of sugars. CH3CH2OH. So you see you have nothing but carbons and hydrogens attached to the carbon that has the OH on it. And that's the key thing, because there's other functional groups that have OHs, but they have other additional things attached to their carbon. Okay, so if you only have an OH attached to a carbon, then it's an alcohol. Alcohols are common solvents. Rubbing alcohol is isopropyl alcohol. Methanol is another solvent, like an ink solvent that is used. You'll oftentimes just see it OH. aldehyde, on the other hand, notice instead of OH, it looks like HO on the end. When you look at the alcohol, compare the two. See how this? It has a carbon, then a hydrogen, and an oxygen at the end. And this is because that oxygen is double bonded to its carbon. So in this one, it's going to look like this. So the carbon has a double bonded oxygen group. I have to add these in. A little challenge. Always on an end. You'll always see aldehydes on an end. They're never going to be in the middle of a chain. That carbon that has the double bonded oxygen and the hydrogen, this over here could be a hydrogen or it could be a carbon. It could be a chain of carbons. That would still leave it as an aldehyde. As long as there's nothing but carbons and hydrogens on this end connected to the carbon, that makes it an aldehyde.
Will alcohol always be on the end?
No, it could be in the middle because it just is one single bond hanging off. So it could be like wherever there's a hydrogen, you could have an alcohol. Okay, so it's not one. Now it can't be in the chain. It's not going to be in like the middle of a carbon chain. You won't have carbon, 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 alcohol, carbon, carbon, because it's only ever going to have one connection. It's only going to be connected to one carbon. Okay, so, but it could be hanging off of a chain, kind of like where hydrogens are. If you think of like any sized organic molecule, wherever you have a hydrogen, you could have an alcohol. But aldehydes are always on the end. So it's one thing to look for. So are carboxylic acids. So you oftentimes see them, they're drawn COOH, which looks like it's a carbon to an oxygen to an oxygen to a hydrogen. But that, in fact, it's a lot like an aldehyde, except that it has that double bonded oxygen and an alcohol group. So that's a carboxylic acid. But because of that, it's also always on the end of a molecule. You won't find it in the middle of a chain. If you have a nitrogen, then it's going to be one of these. If there's a nitrogen, it's either an amine or it's an amide. It's an amine if there's no oxygen connected to its carbon. So this nitrogen is attached to a carbon and it doesn't have an oxygen attached. That's an amine. So the carbon that binds to the nitrogen, if there's no oxygen there, that's the amine. If there is an oxygen there, that's an amide. So you see that this carbon in this one, it has a nitrogen and it has a double bonded oxygen. But the one above, the carbon only is bound to a nitrogen. Ketones are kind of like an aldehyde, but it's in the middle of a chain. So notice that aldehydes have that double bonded oxygen, but they have a hydrogen on their end. So they're always kind of the end of the chain. Ketones are always going to be in the middle of a chain. So you'll have a chain of carbons and there'll be a double bonded oxygen sticking up. So this chain can continue on in either direction. So this one is always in the middle. It's always on a middle carbon. It's never on an end carbon. But what you always want to do is you want to look at the non-hydrogen group. So that one's the double bond oxygen. So you see the carbon it's connected to. Kind of look at the ones that are next to it. Because if they're one next to it's a nitrogen, then it's not a ketone. Now it's an amide. Okay, so you want to look at the carbon that the oxygen or nitrogen is connected to help you figure out if it's like a bigger functional group or if it's a smaller one. Because a carboxylic acid has two oxygens, the amide has an oxygen and a nitrogen group. And so those are a little bit bigger functional groups than just having just a single oxygen. Ethers are where an oxygen spans 2 carbons as part of a chain. So it's not sticking up off like the ketone is, but it's actually in the chain. So you go carbon, carbon, oxygen, carbon, carbon. So it ends up linking 2 carbon groups. But an ester kind of looks like you took an ether and added a what? Which is a what? Do you see that these two kind of look like that? So it sort of looks like you took a ketone and an ether and put them together, and that made the ester. So esters are always like in the middle of the molecule. You'll have carbons on both sides. Carbons coming in one way, carbons going out. You'll always have an oxygen in the chain, but there'll also be a double bonded oxygen there. Last two. Thiols are sulfur containing groups. So there are some proteins that have sulfur. So just remember, if you see a sulfur, it doesn't matter what else is around it. If you see a sulfur, it's a thiol. Sometimes you have disulfides, but really the thiol is the only thing. Just look for the sulfur. When we were talking about alkanes, I said when you talk about hexane, butane, propane, the ANE on the end, that name means all single bonds between carbons. So alkanes, no matter how big they are, they're just going to have single bonds between the carbons. Alkenes, they have at least one what? Instead of all being single, they have at least one double bond. So you will see this. So you'll see sort of a double line. I'm trying to make it look so that you can tell. So you'll see like a double line, that's an alkene. And alkynes have one or more triples. So in that, you would actually see 3 lines. They're not the best lines in the world, but you would actually see 1, 2, 3 lines to indicate that triple bond. They're not the most stable. They're not the most common. Alkenes and alkynes are more reactive than all single bonds. But then that left us with the last one between aromatics and phenols. So the aromatic was the cyclohexane that was a little different because the cyclohexane, as an aromatic, has a single and double bonds that alternate. So we saw that last week, like when we made aspirin in lab. Alternating single and double bonds is called an aromatic group, unless it has an alcohol on it. So if you see an alcohol with an aromatic together, that's a phenol. So those are pretty much all of them. Alkanes, alkenes, alkynes, those are just hydrocarbons, and they only vary really by the number of bonds that they have. Aromatics are those cyclohexanes, but with the different bonding arrangement. So in the rest of this, I did some examples to hopefully help you get a little more comfortable just with picking them out. So what do you see in the first one? When you look to try and pick out a functional group, what you're looking for is not carbons and hydrogen. Like, look for things that are not carbon and hydrogen, because those are the things that make the molecule not just an alkane or an alkene. So in this one, you see what? Okay, so we see this. So you might say that that's a ketone, but what I want you to do is always look at the carbon it's connected to, and then look and see what's next to it. So do you see how this is all connected? So that carbon with a double bonded oxygen and then another oxygen sticking off, and it's in the middle. We've got carbons on either side, so it's in the middle of the chain. This is a what? Yeah. Can you see that that's an ester compared to a ketone or an ether? So look at the one that's on the right. It's a ketone, okay? So it is, you see this double bonded oxygen. Like I said, then look at the carbon it's connected to. The carbon it's connected to is only attached to carbons. So that is a ketone. So you see the difference between the two of them and what you're looking for. What's the next one? Over here down under to the left. It's an ether, an ether. So whenever you see just an oxygen, just one, and it spans two carbons, that's an ether. So notice it doesn't have a double bonded oxygen like that ester does, being able to pick out the differences. I told you if you see the S, what is this? It's a thiol. Doesn't matter if there's one or there's two, it's still a thiol group. The skunky smell. What about there? Okay, you see a nitrogen. If you see a nitrogen, it's an amine or an amide, right? Those are the only two it could possibly be. So, if you look at the nitrogen, find the carbon it's connected to, and then look to see is nothing but carbons attached. If there's only carbons and hydrogens, then it's an amine. But this one has that oxygen, so that makes this an amide. So it's this whole group is considered the functional group. So if you see a nitrogen, look at the carbon it's connected to and see if there's any oxygen there. If not, it's an amine. If there is, then that makes it an amide. So then we can start doing the fun part about starting to look at like multiple functional groups in a single molecule. This is capsaicin. This is like the super hot stuff in peppers, like in your jalapeno peppers and your habanero peppers. This is the chemical that like sets your mouth on fire. So what do you see there? Aromatic. Okay, so you see an aromatic. There's really two things that aromatic could be. If it's all by itself with no alcohol group, it's an aromatic. But if it has an OH, do you see that? Can you pick this out? So if you see the aromatic ring, look and see, is there an alcohol hanging off anywhere? If not, it's an aromatic. If there's an alcohol, then it's a phenol. You see the difference. Do you see any others? You see the nitrogen. So if you see a nitrogen, it's an amine or an amide. Okay, so here's the nitrogen. Okay, it's connected to this carbon, it's connected to that carbon. Do either of those carbons have oxygen attached? Yes. So that makes this whole group an amide.
What is that first group? I thought it had to have alcohol.
So that's just it flipped backwards. So this would be the same as saying an oxygen then connected to a hydrogen. Because if they had OH, then it would look like the oxygen was connected to the carbon connected to the ring. So they're like flipped it over backwards. It's a good question. So same thing, notice this one up here. So it says H3C, and it's just because that carbon is connected to the carbon, then connected, and the next one's a CH3. So they just flipped it over backwards to show its carbon connections, and the hydrogens are kind of on the outside. Okay, you see any more?
Ether.
Yeah. There's an ether, exactly. And you know it's an ether because it's in the ring. It's got carbons on either side, and those carbons don't have any oxygen on them. So that's an ether. And then what's this?
The double bond.
So you call that a, nope, alkene. Right? A double bond is an alkene. Triple bond would be an alkyne. So in this one molecule, there's actually 4 functional groups.
So, I mean, how would you say that?
So if I gave you a couple of molecules, I would just tell you, identify as many functional groups as you can. Usually I'll tell you how many, like there's 9. So like in this one, oh yeah, it's up here. Okay, let's do, so there's aspirin. So aspirin is the one that we made last week. Unfortunately, like as I made this bigger and bigger and bigger, it got worse and worse and like fuzzier and fuzzier. So this is a ring with alternating single and double bonds. So I don't know if you can see that very well.
Can I ask a question? That line is on the outside of the, does that matter?
It's just somebody used some really strange drawing program to do it.
Just meant something else.
No, and in fact in your, like in MyLabs Plus, when you go and draw them, it is not unusual for you to see ones that are like, they're just like this. Have you seen those? Like the lines aren't connected. That's just because of their chem drawing. That's a double bond. Having the 2 lines, I always try to like make mine connect to the end, but that's just the way that their drawing program looks, is it ends up kind of like just looking like this extra line in there. But that would be a double bond. All right, so this is a C, this is an OH, this is an O, and that's a single bond. There's an O up here, and there's a double bond. So I don't know if that helps a little. So anything you see?
It's a phenol.
If in order for it to be a phenol, what does it have?
Oxygen directly on.
It has to have an alcohol group connected to the ring. So that makes this ring a,
Aromatic.
this is an aromatic. What else do you see? Yeah.
Oh, it is, okay.
So do you see this one? Carbon with a double bonded oxygen. You look to see, okay, is it an aldehyde? Is it a carboxylic acid? Is it a ketone? But see how it's connected to an oxygen? So when they're both connected and it's in it forms that span, that's an ester. So what's this one? It's always all the way on the end. It's a carbon, 2 oxygens. One's a double bonded oxygen and one's an alcohol.
Yeah, aldehyde.
Nope. If it was an aldehyde, it would just have a hydrogen on the end.
Alcohol.
Then it would just have an OH. It's a carboxylic acid. So you see that? Compare that to what you've drawn. This one's Tylenol. What do you see in Tylenol?
Aromatic.
There's an aromatic, but
Oh, so I couldn't. It looked like a CH on.
yeah, I know. It's sorry. That's an
a
O.
phenol.
It's a phenol. Because it's an aromatic with an alcohol. Aromatic with an alcohol is a phenol.
Like ketone.
This is the carbon double bonded to an oxygen. This is an N. So N is either or amine.
No oxygen on the carbon. There is one, so it's amine.
It's an amide. So you see, if you see the nitrogen, look at the carbons next to it to see if there's any oxygens on them. If there's a double bond oxygen on any carbon connected to the nitrogen, then that makes it a amide. I did all the pain meds. I did aspirin, Tylenol, and Advil, ibuprofen. So what do you see in this one? Get back down here. Gosh. It doesn't like this at all. There is an aromatic, see right here. Notice that there's no alcohol on that. So that makes it aromatic. And that one's an example. See how like the double bonds don't really touch the ring, but they're still double bonds, just the way they're drawn. What else you see? So where was that one? Okay, so you see this, but see how that's on it too. If it was, this is not a carbon, that's an oxygen. Really need to make these sharper. So it's what? Carboxylic.
Yeah, that one.
Carboxylic acid. Carboxylic. Anything else? The rest are just carbons, so those are fine. Just those two. Saccharin?
There's an alkene and a thiol.
So the sulfur containing, it's a thiol. An aromatic.
Is there two?
And an amide, yes.
Yeah.
See the nitrogen? So you just look to both sides to see. An amide. Now the last one. It's a whole lot of rings going on.
Aromatic.
That's an aromatic.
Is there three?
You're like, I got one. You got that one down. See the ring? No alcohol. It's an aromatic. I got
So are
that.
they all
Okay.
aromatic?
So, well, how many? This is 1, 2, 3, 4, 5, 6,
Okay.
7. So that's actually a cycloheptane.
So there's two aromatics.
Actually, a cycloheptene because it's got a double bond in there. So no, that one's not. But what about this one?
That one is.
Yes. This is also an aromatic because it's just got a chlorine hanging off. So that's not a special name. What's this? It's an amide. Yep. Can you see the amide? See the nitrogen. Whenever you see a nitrogen, it's an amine or an amide. All you're looking is, do adjacent carbons have a double bonded oxygen? That's how you can pick that one out.
So the double bond doesn't have to be directly off that nitrogen.
No, it's not gonna, it wouldn't be directly off the nitrogen. It is on the carbon next to it. Because look at this one. See this one here? Same thing. So it's the carbon next to the nitrogen. So you got a carbon with a nitrogen and a double bonded oxygen to make an amide. So what's one more? What's that? Just a single nitrogen or just a nitrogen? Nothing's fancy on the other ones. It makes this a the amine. Amines, amides. So the one that's all the way at the top is one that is, it's not a real molecule. I just drew it. Because I was like, because every time I give like examples, people will be like, well, how do you pick these ones out? Like, you know, so this one, there's actually 9 functional groups in this one molecule. So what I want you to do is just take a minute, see how many you can find in circle, and then we'll go through them. I think I almost got it all on the page. There. Do I have a pencil? I usually do. Find in circle. See if you can find all 9. Use your sheet that I gave you. Found 7, 8, right?
maybe.
Just tell me one. Just like what part of the molecule?
Ester.
Okay,
Top left.
this one? Yep, this one's an ester. Everybody get that? Okay, what's another one, Sam?
The sulfur at the bottom's a diol.
Uh-huh. So see here? Which one? Did you get one?
Ketone.
Where?
Double O. With a CHC.
Here?
Yes.
Mm-hmm, you're right. Ketone.
This is another ketone at the top.
Where?
Double bond carb at the very
Like,
top.
okay, like upper right?
Yeah.
This one.
Yeah.
Okay? So what's that one?
Ketone.
Ketones are always in the middle of a chain. It's not an alcohol, it's an aldehyde. Compare that. Look at your chart. Do you see that you've got that double bond oxygen and a hydrogen? Okay, so when it looks like it's that double bond oxygen on the end, hydrogen on the end, that's an aldehyde. Mm-hmm.
Is the one under it at the end a carb
Yes.
really
Car, box, and then ilic. Car, box, and then ilic acid. Mm-hmm.
Is that a alkyne at the bottom with the three triple? I mean, not triple. I was looking at
Where?
They're double bonds, so that would be alkene.
Where?
At the bottom left.
Down here?
Yeah.
No, that's just, this is a stray mark. That's, but I don't know where that other little blue mark came in.
Okay.
I went in and added hydrogens because I tried to do all the hydrogens on here, and while you were working on it, I was like, oh no, I missed. What else?
Would that be an
Yes. Mm-hmm. It is exactly.
There's a mine or a mean
Okay, which one?
on the last one.
Uh-huh. Down here. See, notice that this carbon has carbons attached to it. Nothing but carbons and hydrogen attached to the carbon with the nitrogen. So that makes this a amine. And then going up, do you see the difference here? So this nitrogen has a carbon with a double bonded oxygen. So this is the amide. Phenol. Mm-hmm. Is that it? Yay. It's not terrible. Okay. So there is an identification of functional groups as part of the post-lecture homework in chapter 4. So just go through, but sometimes it's more than one. Sometimes you can have more than one functional group in a molecule. Really, you're looking for things that are oxygens and nitrogens, or you're looking for them in different kinds of arrangements, or those cyclohexanes with the aromatic arrangement. The hardest is really the oxygen, because with the oxygen, you got to figure out what else is it connected to. Is it just an alcohol, or is it a double bonded oxygen? Is there other groups around it to be able to pick them out? So hopefully that helped just a little bit, because I know last time everybody was looking at me like, why is she doing this? So that's why I was like, well, let's just summarize all of those and go back again to make sure that everybody's like on the same page. Well, back up. So lipids, the first of the nutrient groups, we're going to talk about lipids, carbohydrates, and proteins. Those are the three main nutrient groups. Most people call these fats, but really its technical term is lipid. They have this on the end. What is this? So that group is a carboxylic acid. So lipids are long chains of carbon. This one here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons. And that's actually a small lipid. They can be up to 24 carbons long. That is why you oftentimes see them written in their skeletal structure, because the skeletal zigzag structure is a whole lot faster than saying CH2, CH3, 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 and just over and over and over again. So that's why you'll see it oftentimes in the zigzag pattern. But notice the carboxylic acid on the end. if all of the carbon-to-carbon bonds in the zigzag chain are single carbon-to-carbon bonds, they call that saturated. Saturated fats most commonly come from animal sources. And can you see how they make a really straight line? The zigzag forms this nice uniform arrangement. You can pack saturated fatty acids together tightly at lower temperatures and they'll become solid. This is why your animal fats tend to be solid at room temperature, because they can pack in so well. Unsaturated though, remember we said alkenes and alkynes, those are called unsaturated hydrocarbons. If they're unsaturated, it means that they have one or more double bonds between the carbons. So there's the first one. This is a mono unsaturated fat. Mono just means one. Unsaturated means it's got a double bond. Notice that it is in the cis arrangement. So see how where the double bond is, both of the bonds stick up from it. But what it does is it makes them look like this. When you pack or pile a whole bunch of unsaturated fatty acid chains together, they don't pack in very well. They're not very straight. They have a bend. So this drawing that I have right here, it makes the chain looks like it's got a bend. So you got like a zigzag, then a bend, and then a zigzag. They can't pack in because of this double bond. This is why they're liquid at room temperature. They are most commonly found in plants. So plants live in the environment that they're in, and they would like to keep their liquids softer at room temperature. Whereas animals, they're always higher than room temperature. They have body temperatures of about 100 degrees Fahrenheit. So their lipids are liquid at 100 degrees, but they wouldn't be liquid at 75 degrees in this room. So that is why animal fats can be saturated, because they're at higher body temperatures, so they stay liquid at that 100 degrees Fahrenheit. Whereas plants, they would end up being all stiff and solid if they didn't have unsaturated fatty acids. So saturated fatty acids typically come from animal sources, and they tend to be solid at room temperature. So you can think of butter, bacon grease, lard, all the meat drippings, when it's on your plate, they all congeal. Whereas plants, they're oils. Rather than being the solid fats, they're oils. They stay liquid at room temperature because of that double bond. And if they're polyunsaturated, then they may have 2 or 3 or even 4 double bonds, and that creates a super bended looking molecule. In fact, some of these fatty acids are considered essential. So when they talk about nutrients that are essential nutrients you have to get in your diet. So there's 2 essential fatty acids. So fats are actually required in the diet. You don't have to have them in really high amounts, but you do have to have some, or you'll begin to show deficits. You'll begin to show deficiencies because of the lack of. So these carbons, when we're talking about lipids, we're talking about 12 to 22 carbons long. They can be very long chains. They have the carboxylic acid group at the end. You can divide lipids into fats and oils because of their composition. So here, stearic acid is a really common animal fat. Stearic, like steers, like cows. So stearic acid, all saturated, all single carbon-to-carbon bonds. The other ones, though, notice these 2. Has anybody ever bought coconut oil? What does it look like sitting on your shelf?
Solid white.
Yeah, it's like white, creamy white, soft though. You know, it's not like really hard. It's pretty soft, but it has a high amount of saturated fats because coconut and palm, they're called tropical oils. They grow close to the equator where it's always warm. So those plants can use saturated fats because their temperature is always warm. They wouldn't do so well if you tried to plant them in northern areas, because they would make these types of lipids. So they call these ones tropical. But you can really kind of like think to yourself, most of the time, saturated fats are in high concentration in animal products. And they're going to be all single carbon-to-carbon bonds. So if you look at, so here is lard, butter. Those two, along with coconut and palm, see how much saturated fat is in them? That's the blue. So those are much higher in saturated fat. That is why these tend to be solid at room temperature. But when you look at the oils, soybean oil, olive oil, corn oil, canola, notice that the green, the amount of green and red is much higher than the blue. So the green and the red, these are those double bonds. So these are the unsaturated fats. The more unsaturated fats, the more you have the liquid at room temperature. So here's a couple so you can just see what I mean by the monounsaturated, like palmitoleic and oleic acid. Just a single double bond. But do notice that the shape is that they stick up. That's a cis conformation. Linoleic and alpha linoleic, those are your omega-6 and omega-3. Maybe you've heard of those because they are ones that people that are even trying to eat like a low-fat diet, they do encourage them to take supplements of omega-3 and omega-6. Those are actually, they're required in your diet. So you do need them on a regular basis. People that are on low-carb diets sometimes run into problems with having low amounts of this, again, because they don't eat a lot of the beans or any of the grains, and so they may be missing that way too. So those are the polyunsaturated. Just poly means many. So you see one has 2, one has 3, and the one down at the bottom actually has 4. Get plenty of that from eggs and lard. But these ones are all liquid at room temperature. So that's an example of like where you would see functional groups in the lipids. We're going to come back and talk about cis and trans. We're going to talk about fats again in upcoming chapters. They just sort of like drop it and then go off and do something else. They'll come back and talk about it though. So the last topic is all about these special isomers that have carbons that make them really different than normal. So chiral carbons are carbons where you have 4 different groups connected. So a carbon that has 4 different groups. So in this one, I have a carbon with a hydrogen above, an OH to the right, an amine group below, and then a methyl group to the left. So all 4 of them are different. So in lab, we actually put together something very similar and we made the mirror image. And what you found was you can't lay them on top of each other. So they're non-superimposable, but they do have the same bonding. It's just that because they have a carbon with 4 different groups connected, their mirror images are not identical. So those mirror images are called enantiomers. And my best example for you is like, it really makes like a right-handed and a left-handed molecule because your hands are kind of like chiral carbons. So your hands are put together the same, but in one looks like the identical mirror image of the other, but you can't lay them on top of each other. So they're not identical. If I flip it, then that's the palm and sole, the palm and the back of my hand. They're still not exactly the same. And so the same thing goes with these. So I have an example, and this is the one that they have here. So the first one, this is just spearmint gum. So I just got spearmint gum and cut it in small enough pieces to be able to put it in the tube. You can take the lid off and give them a smell. The second one are caraway seeds. So caraway seeds are the seeds that they put in rye bread. So those little like sliver black. These are the molecules that give the aroma to each of those are actually enantiomers. One molecule is like the right-handed version. The other one is the left-handed version. So like caraway seeds have kind of like a spicy sort of smell to them. Spearmint is minty. Like totally different. In fact, so that means that the receptors in your nasal passages can tell the difference between these two molecules that otherwise have the same number of atoms, put together exactly the same. The only difference between them is that one is the mirror image of the other, and they have a chiral carbon. So there's that rule. If you're looking at a carbon, you have to have 4 single bonds. So any carbon with a double bond can't be chiral. Any carbon with a triple bond can't be chiral. Okay? It has to have 4 single bonds, and all the groups connected have to be different. So in this one, looking at this molecule, this carbon, this green carbon, when you look at it and you see CH3, you will throw that one out automatically because it has 3 hydrogens. Okay, so this carbon here can't be chiral. It's got 3 hydrogens connected. This carbon, though, is the one that they show because above you have an alcohol, to the right is a hydrogen, to the left is a CH3 group or a methyl group, and below is a CH2CH3 group. That would be like an ethyl. Okay, so all groups connected, and it's not just the carbon next to it, it's the whole piece. Okay, so it's the entire piece connected, below, above, to the left, and to the right. So you see that those are all different. And that's the biggest mistake people make, is they only look at like what it's connected to directly, but it would be the entire part that it's connected to. So 4 single bonds, every single group connected is different. That will create mirror images that are not superimposable, and that's going to actually give you 2 different versions of the same molecule, like a left-handed form and a right-handed form. So here we're going to look at some. So this top one, this top left, are there any chiral carbons in this molecule?
No.
Why?
They're all the same.
They all have at least what?
3 or 2.
To what? They all have more than one hydrogen connected. So do you see, if you look at this one, 3 hydrogens. You look at this one, hydrogen above and below. Look at this one, hydrogen above and below. Hydrogen above, below, and to the right. So there is no chiral carbons in this one. Okay? What about the one over on the right?
No.
So what about this one? No. What about this one? So with each one, you're always looking at the entire group above, below, to the left, and to the right. So the group above is an alcohol. The group below is a hydrogen. The group over here is a CH3. Okay. The group over here is a. So is that chiral? No, there's 2 methyls or 2 single carbon groups. And then what about this one over here? The last one. No, why? Because it's got hydrogens. Okay, so that one would be no, because it has 3 hydrogens. So this one, there's no chiral carbons. Chiral carbons are kind of special. Like, it's not that normal for you to have 4 different groups. It's much more common to have carbons with multiple hydrogens. So you're not going to see them all the time. Look at this one down below. Okay, so what's this one got? That carbon has, if you see CH2OH, remember that this carbon is going to have 4. That means that there's one is an H, one is an H, and one is an OH. So that would be no, because it has 2 hydrogens. What about this one? No, I said it has to have 4 single bonds. Okay, so you can throw those ones out all the time. So then, what about this one? So to the left, I have an H. To the right, I have an OH. Above, I have a 2 carbon group, 5 hydrogens, 2 oxygens. Below, 2 carbon group, 5 hydrogens. Wait, how many? No, I only have 3 oxygens, or 3 hydrogens above, 5 hydrogens below. So are they different? Are the two groups above and below put together differently?
Yes.
So above and below, and to the left and to the right. So those are all different. This is a chiral carbon. So that means that I could make a mirror image of that molecule and it would not be superimposable. And they may have different functions. They may have different activities. What about this one? Let me change the colors. It's easier, I think. What about the blue carbon? So to the right is a hydrogen, to the left it's an alcohol. Below is a single carbon group, and above is 3 carbons. So it's everything above. That's 1, 2, 3, 4. So is that chiral?
Yes.
So that's a yes. So that one has 2 chiral carbons. How about this one? A CH3. No, because it's got 3 hydrogens. It has to have 4 different groups. What about this one? So when it's CH, remember that just means the H is up here. So above is a hydrogen, below is an alcohol, to the left is a CH3, to the right is a 2 carbon group with an alcohol. So yes, that is a chiral carbon. What about the one next to it? This carbon. So that H would be sticking up here. It's just written in its condensed structure. CH3 to the right, OH below, a 2 carbon group to the left, and a hydrogen above. So yes, those are all different. What about that one? No. So there's 2 chiral carbons here. And those will be the ones that I kind of stick with. I'll try and give you ones that have like the more of the Lewis structure to them. So this one down here, this is actually vitamin C. It's ascorbic acid. It's important so your teeth don't fall out. But when you look at this one, this is a carbon, this is a carbon, these are carbons. So what's this one? So we'll just take each one. So this carbon has how many hydrogens? See how there's only 2 lines to it? That means how many hydrogens are there? 2, because it's got to have 4. So that would be like this. So you know that that one's not. What about the next one? So this carbon has this group above, and OH. This whole ring structure thing would be the 3rd. What's the 4th thing? An H. That's its chiral carbon. In the ring structures, it's rare that you have ring structures that are chiral carbons. Just because like these carbons, they've got double bonds. This one's got a double bond on it. But that one right there, there's 1. So that means vitamin C actually has like a pair. There's a left-handed version of vitamin C and a right-handed version. So this actually can affect how a molecule works. So the Food and Drug Administration, the FDA, they have required that every drug that is made, you have to know their chemical formula, you have to know the chemical structure. And if there's any chiral carbons, you have to generate the right and left-handed versions of them. So you have to synthesize both. You have to synthesize all enantiomers of a drug, and they all have to be tested. So things that they found, Parkinson's. So Parkinson's disease is where you have a decrease in dopamine in the brain. So the part of your brain that makes dopamine begins to deteriorate. And so you begin to have tremors, shaking. You have this memory loss all associated with neurological processing. You end up having, a lot of times people have like Alzheimer's sort of dementia, anger, frustration. I mean, it's really frustrating when you want to say something and you can't think of it. And so all of those behaviors all come into play. Eventually, though, someone with Parkinson's is going to end up being in a wheelchair, and then they're going to end up bedbound, and they're going to be unresponsive because they have no fine motor control. So they can't pick things up, they can't feed themselves, they stop eating, the whole 9 yards. They found that there was a drug that they could give them. If they gave them dopamine, which is the chemical in the brain that is not made, Dopamine doesn't cross the blood-brain barrier. So you can give it to the patient all you want. It can't get in and around the neurons to be able to be used. But they found that the molecule that's used to make dopamine, called DOPA, that molecule does cross the blood-brain barrier. And what they found is that they gave the patient just one, the left-handed form, because I've got the little piece up here. There's your chiral carbon. So there's like a nitrogen below. There's a carboxylic acid group up to the right. There's a hydrogen, and then there's this whole group. So all four of those are different. They had to give them the L, the left-handed form. They call them L and D. L is like levorotary, which really means like the left-handed type. D is dextrorotary, means like the right-handed type. They had to give them the left-handed type. The brain wouldn't use the other one. So these molecules have shapes that then are very specific in terms of being able to be used, much like a lock and key. So having just a slight difference in the way the teeth of the key is will end up allowing it to work or not work. Same thing here. Tylenol. Tylenol is another example. Acetaminophen has a chiral carbon. One form of Tylenol doesn't do squat. It doesn't help at all. The other form reduces fever, reduces inflammation, helps to alleviate pain, all the beneficial things. And so one form, no activity. The other form is used as a medicine and has all of the beneficial features. So the Food and Drug Administration, when a new drug comes out, you have to know the structure of the molecule. You have to be able to determine if there's any chiral carbons. You have to synthesize all of the enantiomers, like all the left-handed and right-handed versions of the drug, depending on the number of chiral carbons. You have to test every single one. And the reason that this has become so strong is because of something that happened in the 1950s. So in the 1950s, big complaint was that women during that first trimester of pregnancy that they had morning sickness. And so morning sickness is negative because you can get dehydrated, especially if you're excessively vomiting. You lose weight, and that's really not optimal for a developing fetus. So they're working on trying to find drugs to alleviate morning sickness, and they came up with a drug called thalidomide. So thalidomide, when they initially synthesized it, they got this form. So in initial synthesis, they only made one enantiomer, didn't look at the structure, didn't realize, and if you look, it is this one. That carbon is a chiral carbon, but under early test trials, they just synthesized one form. Ran through and did tests. They found that it really helped to cut down on nausea, cut down on morning sickness, means that moms lost less weight, babies had higher birth weight values. So they began to then mass produce it. So when they mass produced it, it was primarily released in Europe because this was all done developed all in Germany. But when they did, they actually began to make both forms. So they made, in testing, they only really tested the left-handed form. When they went to upscale and make lots of this, they ended up creating both enantiomers. So the pills that were distributed were not the same medication, very close, but didn't include both of those enantiomers. So the one on the left was really good at helping to cure morning sickness. The one on the right, because it was given during the first trimester, the one on the right is actually teratogenic, which means that it has the ability of causing birth defects. Given in the first trimester, it actually limited or ended elongation of the buds that are going to form arms and legs. And what they ended up with 10,000 babies that were born in Germany, in the areas of Eastern European, that area. About 10,000 babies were born that were missing limbs, didn't have arms and legs, or had little flippers for arms and legs. It took about 18 months So like these mothers are taking it in the first trimester. So they're not even going to give birth to these children for another 7 months. And so 6 or 7 months, they've already had other women taking this medication to relieve it before they like started having these numbers increasing. And so it was almost 18 months before they pulled it off of the market. So that's 10,000 babies that like wouldn't be able to walk, couldn't feed themselves, required like round-the-clock care. A lot of them then all of their pelvic floor structures didn't form right, so a lot of them had to have like colonoscopy bags and everything else. But this was like a big like shock that it slid through, and nobody actually got or looked at the structure of it, of thalidomide, and then noted that there was actually a chirocarbon in it and required the formation of both of them. So a lot of changes went in after this happened, so that now that's it. Like, and when you're starting to put in like your drug to go through drug trials and things like that, you have to know the structure. You have to identify like the exact molecular structure. If there's any chirocarbons, they have to be noted. And so you have to then proceed to synthesize and separate all the enantiomer types. So they all have to be tested in order for the drug to be able to go even further on into human trials, all because of stuff like this that would happen prior to. Which is just sort of an interesting one. All right, so I'll quit there. This finishes chapter 4, okay? So we have class on Wednesday. So Wednesday, we're gonna talk in chapter 5, really just about like types of chemical reactions. Like there's no math in any of it, it's sort of theory. And I think it's like synthesis and decomposition, exchange reactions. They're pretty almost intuitive kind of material. So start working on like getting your card ready. If you have any questions about any of them from chapters 3 and 4, write them down, jot them down. If there's any others, we'll go through and do a little more review. Like we'll do a few more isomers, maybe some more chirocarbon identification in the beginning for Wednesday, but then we're going to go on into chapter 5.